Okay, YouTube, this is my first video in my module on solving equations, in which we're really going to focus on solving linear equations. So that is equations of the form ax plus b equals 0, where we do not allow a to be 0, because of course if a were 0 here, then you would just have b equals 0, which it could be possible, but might also be an absurd statement. So we say linear equations in one variable of this form ax plus b equals 0, and the reason why we refer to them as being linear is because if you are to graph all of their solutions, they appear to occur along a line. So for instance here, if I had this equation here, 3x plus 6 equals 0, and I wanted to solve it, I could go graph it. I could say, look, all of its solutions occur along this line, okay? So when we solve a linear equation, let's go ahead and start with some vocabulary here. We're attempting to find all values, okay? It could be no values, or one value, or more than one value, but all values for a variable that produce a true statement when substituted into the equation for the variable. And this is very important that we know this word here, this set of words, but we say such values are referred to as solutions of the equation, but also we call them roots, we'll call them those also. So let's consider this equation right here. This looks like what I've got written up here, 3x plus 6 equals 0. And the thing I want to notice here is that the solution set for this, if I said, well, what's the solution for it? I'm really asking what number when substituted into this equation for x, like right here, would give us a true statement. You'll notice that if we were to just plug in -2 right here, okay, we'd say 3 times -2 is -6. And we get -6 plus 6 is 0. So we get 0 equals 0. So this is what we mean by a solution. It produced this true statement right here, okay? So we say the solution set for x. You'll notice that I say it's a set, but x is -2. And so you'll notice that we could write x as -2, and we often do write this, but I want to get in the habit of saying that the set of solutions occurs in this little bracket here, and we say everything in this set is a solution for this equation, whereas the only element in the set is -2. So really quickly, before we go on to solving an equation on our own, let's look at this up here. I say the following equations are all considered to be what we call equivalent equations, okay? So equivalent equations are equivalent because they share the same solution set. So if I plug in -2 here, we observe that we get 0 equals 0. If I plug in a -2 here, I get -6 equals -6. And if I were to plug in a -2 here, I get -2 equals -2. The idea, though, is all of these being equivalent, what we want to do is take an equation like this and transform it piece by piece until we get it down to a statement that looks like this. X is equal to some number. So in other words, our goal is to isolate the variable for which we're solving, okay? In this case, I'm going to say isolate x, all right? So now that we know this, let's go ahead and talk about what ways we can use to generate equivalent equations so that we can isolate a variable. So there are 4 very simple things we just want to mention here, but basically when it comes to what things can I do to an equation that won't change the fact that the solution set is the solution set, one way to do it is we could simplify each side of an equation. So for instance here, you'll notice that they have an expression 3 times x minus 6. Well, we notice we can distribute that. So we could simplify it, and we get something that looks like this here on the left, and then on the right we say 6x minus x. Well, we could certainly go ahead and combine like terms. So those are things we can do. We are also allowed to add or subtract the same real number to both sides of the equation. So if I had something like this, 3x minus 18 equals 5x, then perhaps what I want to do is subtract 3x from both sides. We could do this vertically. We could stack them, do it vertically. Or we could do it horizontally as they've got listed here. But what that essentially does is it gets this constant on the left side by itself. And we say on the right side, all of my x's are on one side. And then furthermore, we can multiply or divide both sides by the same number if they're equal anyways, and we can do the same thing to both. So with this statement that we leave off on here, it would be appropriate to say, well, I'm multiplying x by 2, let's divide both sides by 2, because then 2x divided by 2 would give me 1x. And then notice here, I get this statement, and last but not least, I am allowed to interchange the two sides of an equation. They are already equal. So let us use these properties here to solve a couple of linear equations, starting with this one up in the top right here. We say 4x plus 5 is equal to 29. So our goal is to get x by itself. Now, in order to do this, we'll simplify both sides first, and you'll notice that not always is that something you have to do just because it's a step over here, but both sides are really simplified. So what we want to do is get rid of this positive 5 here, this addition of 5, and also this multiplication of x by 4. And it is always appropriate to undo your addition and subtraction first. So I'm going to go ahead and subtract the 5 from both sides. I say, well, then 4x is equal to 24. And if I divide both sides now by 4, okay, that's something I can do and still have the same solution set, then I get x equals 6. So we would say, or the solution set is the element 6. It's the only thing that's in the solution set. So the 2 ways we want to write it, let's get used to this one on the right. And then this one down here. Now I say solving, more involved linear equations in one variable. Just this, step 1, it says simplify the algebraic expression on each side by removing grouping symbols and combining like terms. You're going to notice this equation down here has x's on both sides, and there's some simplification that needs to be done. But after you simplify both sides, what we're going to do is we're going to collect all the variable terms onto one side, and then we're going to isolate the variable and solve, kind of like we did up here. So basically, this was already simplified and had all the x's on one side of the equation. This one just doesn't have that yet. So the first thing we'll do is we'll simplify both sides here. I notice I can distribute, so I would get 8x's plus 4 constants is equal to 29, plus now my 3 times 2x was 6x, and we say 3 times a negative 5 is negative 15x. So I'm going to combine like terms here, and we say, well, now I still have x, 8x plus 4 on the left side. On the right side, 29 minus 15, I think that's 14, so we say 6x plus 14. Now, in terms of getting all the x's on one side, we just did step 1. Let's get all the x's on one side here, and it's kind of a nice thing to go ahead and subtract the lesser of the two, or add the lesser of the two to both sides, depending upon what you have, because then you turn out a positive coefficient of x. Okay, so I get this 14 here. So if I were to now subtract 4 from both sides, of course, 14 minus 4, so that's supposed to be a 4 there, would lead us to the fact that we get a new equivalent equation where we'd say, okay, well then I get 2x is 10, and then dividing both sides by 2 would produce an equivalent equation. We say x is equal to 5, and so our solution set here, we'll say, is the set containing the element 5. If we were to now check this, and this is the first time I've done this in this video, but plug it back in, we would get this. We would get 4, 2 times 5 plus 1, and this is just me substituting in for all of my x's any of these solution values that we found, 2 times 5 minus 5, and we'll simplify this. So I would get here 4 times, this is 10 plus 1 is 11. On the right side we get 29 plus 3 times, this is 10 minus 5 is 5, so we'd say this is 15 here, 15 plus 29. This gives us 44. On the left side we have 4 times 11 is 44. So this is the true statement we wanted to get. Cheers.